The roof that Martin Lindholm built on his Wyoming cabin in 1918 looked like he'd started building one roof, gotten confused halfway through, and decided to build a second roof on top of the first one with a strange gap between them. While every other homesteader and trapper in the Wind River Range had constructed single-layer roofs with shingles laid directly over rafters, Martin had built two complete roofs separated by exactly 3 3/4 inches of empty air space. The bottom roof had rafters, boards, and tar paper, then 3 3/4 inches of nothing, then another set of rafters, boards, and shingles. From the outside, the cabin looked oddly tall. From the inside, looking up at the ceiling, you could see the gap between the two roof layers if you knew where to look. It appeared he'd wasted lumber, wasted time, and created a structure that made no sense whatsoever. "You've built two roofs," said Carl Hansen, Martin's neighbor whose cabin sat in a clearing half a mile to the east. "Why would anyone build two roofs? One roof keeps the rain out. Two roofs just means you wasted wood and made your cabin taller for no reason." Martin was on a ladder, making final adjustments to the ventilation blocks he'd installed at the eaves, small wooden spacers that kept the 3 3/4 inch gap open while preventing birds and mice from nesting in the space. Two roofs with an air gap between them. The air gap is insulation. Better insulation than anything you can buy. The gap keeps heat from escaping in winter and keeps heat from entering in summer. Best thing you can do for a cabin. Air isn't insulation. Air is nothing. You've built a gap of nothing between your roofs and you think that will keep you warm. Martin, you've been alone in the mountains too long. You're not thinking clearly. Air is the best insulation that exists, better than wood, better than cloth, better than anything. But only if the air is trapped and can't move. If air can circulate, it carries heat away. If air is trapped in a thin layer, it can't circulate. It just sits there, being the world's best insulator. That's what this gap does. Traps air, prevents circulation, creates a thermal barrier. 3 inches of air versus 8 inches of solid wood in a normal roof. The wood is more insulation. Obviously, your gap theory doesn't make sense. Wood has an R value of about 1.25 per inch. 8 inches of wood has R value of 10. My air gap, 3 3/4 inches of trapped dead air, has R value of 14 to 16. More insulation in less space. Much more effective. Carl stared at the double roof, trying to make sense of it. R value, dead air, thermal barriers. You sound like an engineer. Where did you learn this? I was an engineer in Sweden. I designed buildings for 5 years before I came to America. I know how heat moves. I know how insulation works. Everyone here builds roofs the way their grandfather built roofs. No one thinks about the physics. I think about the physics. This double roof with the air gap will keep my cabin warmer in winter than any normal roof, 30 degrees warmer, maybe more. 30 degrees warmer than my cabin? That's impossible. We'll have the same stoves, burn the same wood. My cabin is well built. You can't be 30 degrees warmer just because you wasted lumber on a second roof. The roof is where most heat escapes. Hot air rises. It reaches the ceiling. In your cabin, it goes right through the ceiling and roof and escapes. Maybe 10% stays in. In my cabin, it hits the ceiling, tries to escape, but encounters the air gap. The air gap is a barrier. The heat can't cross easily. 90% stays in. Huge difference. I think you're going to find out that your engineering theories don't work in the real mountains. Winter will prove that. Winter will prove I'm right. Want to make a wager? Coldest week of winter. We measure cabin temperatures. Same outside temperature. We see who's warmer. Loser admits error publicly. You're on. When your two-roof cabin is freezing and you're burning through wood trying to stay warm, I'll enjoy reminding you that I predicted it. They shook hands. Carl was confident. Martin had built something weird and overcomplicated. Reality would correct his theories. Martin was equally confident. He'd done the calculations. He understood heat transfer. His double roof would outperform conventional roofs dramatically. Other neighbors had similar reactions. The consensus was clear. Martin had overthought the problem and created an absurd solution. Two roofs separated by a gap of air made no sense. It violated common sense. It wasted materials. It would fail to provide any benefit. Some people thought Martin was showing off, trying to prove he was smarter than everyone else with his engineering knowledge. Others thought he was applying theories that worked in Sweden but wouldn't work in Wyoming. A few just thought the whole thing looked stupid and left it at that. Martin ignored all of it. He'd studied building science extensively. He'd read everything available about heat transfer and insulation. He understood that the conventional wisdom about roof construction was wrong. People built thick, solid roofs thinking mass provided insulation, but mass without air gaps provided minimal insulation. A thin air gap provided enormous insulation. The key was getting the gap dimension right. Too small and you didn't have enough insulation value. Too large and convection currents would form in the gap, carrying heat across and defeating the insulation. The optimal gap for a horizontal surface was 3 to 4 inches. Large enough for good insulation, small enough to prevent convection. Martin had calculated 3 3/4 inches as optimal for his climate and cabin dimensions. The construction had taken most of the summer of 1918. First, he'd built a conventional roof. Rafters spanning from wall to wall, rough sawn boards nailed across the rafters, tar paper over the boards for moisture protection. This created the bottom layer, the ceiling of his cabin. Then came the critical part. He'd built a second set of rafters sitting on top of the first roof. These rafters were 3 3/4 inches tall. They ran perpendicular to the lower rafters to create a cross-braced structure. The spacing between upper and lower rafters was exactly 3 3/4 inches everywhere. Constant gap. This was essential. Varying gap dimensions would create convection currents in some areas. On top of the upper rafters, he'd laid more boards, then shingles. This created the outer roof, the weather-facing surface. Between the inner ceiling and the outer roof, a 3 3/4 inch gap filled with trapped air. The gap was sealed at the edges but had small vent holes at the eaves and peak. These vents allowed moisture vapor to escape. Trapped air needs to be dry air to insulate well. Moisture would condense in the gap and reduce effectiveness. The vents were tiny, just enough to allow moisture out, not enough to allow significant air circulation. The total cost in additional materials was approximately $25. Extra lumber for the upper rafters and boards, extra nails, extra shingles. The labor was significant. Building 2 roofs took twice as long as building 1. But Martin was convinced the investment would pay off. The first test came in late September when the temperature dropped to 40 degrees Fahrenheit. Martin lit a moderate fire in his wood stove, not trying to heat aggressively, just maintaining comfortable temperature. Within 2 hours, his cabin was at 68 degrees. He let the fire burn down and go out. Over the next 6 hours, the cabin temperature dropped only 4 degrees. From 68 to 64 degrees. The rate of heat loss was remarkably slow. The double roof was holding heat in. Martin estimated that a conventional cabin would have lost 15 to 20 degrees over the same period. His cabin lost only 4 degrees. The insulation was working exactly as calculated. Carl Hansen visited in early October. How's the 2-roof cabin working? Better than calculated. The heat retention is extraordinary. Want to compare cabin temperatures? They both had thermometers. Carl's cabin was at 55 degrees with no active fire. Outside temperature was 45 degrees, a 10-degree differential. Martin's cabin was at 64 degrees with no active fire. Outside temperature was 45 degrees, a 19-degree differential. Carl was skeptical. Your cabin is new, better sealed, better chinked. The roof isn't the only factor. My walls and floor are identical to yours. Same logs, same chinking, same construction. The only difference is the roof, and my cabin is 9 degrees warmer than yours with no fire. That 9 degrees is entirely due to the roof. It's early season, mild weather. Wait until real cold comes, then we'll see. November brought colder temperatures. Martin's cabin continued outperforming expectations. With one fire per day, he maintained 65 to 70-degree temperatures. The heat stayed trapped by the double roof. At night, temperature dropped only 8 to 10 degrees despite no active fire. The thermal retention was spectacular. Carl was burning wood twice daily and maintaining 60 to 63-degree temperatures. His cabin lost heat quickly when the fire burned down. He was starting to suspect Martin might be right about the roof. December 1918 brought severe cold to Wyoming. On December 12th, the temperature dropped to minus 15 degrees Fahrenheit. On December 13th, minus 22 degrees. On December 14th, minus 30 degrees. The cold settled in for a week. Wood stoves across the region burned constantly. People fed them around the clock. Cabins struggled to stay above 50 degrees. The cold was overwhelming conventional construction. Carl was burning approximately 1.5 cords per week. His cabin was averaging 48 to 52 degrees. He wore heavy clothing indoors. He never felt truly warm. The constant fire tending was exhausting. On December 16th, Carl trudged through deep snow to Martin's cabin. He wanted to check on his neighbor, and he wanted to see whether the double roof was performing as Martin had claimed. He arrived and knocked. Martin opened the door wearing a light wool shirt. No coat, no hat. "Carl, come in. Close the door quickly. Don't let the heat out." Carl stepped inside. The warmth hit him immediately. It was genuinely warm, actually comfortable. He stood there letting the warmth soak in. He'd been cold for days. This felt miraculous. "What's your cabin temperature?" Carl asked. Martin gestured to the thermometer on the wall. 79 degrees. 79? Outside is minus 30. That's a 109-degree temperature difference. How is that possible? The double roof. It's holding almost all the heat in. Very little escapes through the ceiling. I fire my stove twice a day, morning and evening, 3 hours each time. The cabin stays warm all day and most of the night. I sleep comfortably. My cabin is 48 degrees. You're 79 degrees. That's 31 degrees warmer. 31 degrees with the same stove, the same wood. Just a different roof. Not just the roof, but yes, primarily the roof. In a conventional cabin, 50 to 60% of heat loss is through the roof. Hot air rises. It concentrates at the ceiling. If the ceiling and roof have poor insulation, that heat escapes. Your cabin is losing enormous amounts of heat through the roof. My cabin isn't. The air gap traps it. How much wood are you burning? About half a cord per week in this extreme cold. Less than half what you're burning. Carl sat down heavily on Martin's chair. He'd lost the wager. Dramatically. Martin's cabin was 31 degrees warmer, using a third of the wood. The double roof had performed exactly as Martin predicted. Better, actually. Martin had predicted 30 degrees warmer. He was achieving 31 degrees warmer. I've lost the wager. Your cabin is warmer. You're using less wood. I don't fully understand how trapped air can insulate better than solid wood, but the evidence is undeniable. The science is straightforward. Air molecules are far apart. Heat transfers through conduction from molecule to molecule. Fewer molecules means slower heat transfer. Solid wood has many molecules packed together. Heat transfers through it easily. Air has very few molecules per volume. Heat transfers through it very slowly, but only if the air can't move. Moving air carries heat by convection. Trapped air can't move. It's forced to transfer heat by conduction only, which is very slow. That's why the gap works. Can you help me add a second roof to my cabin? We can't add it to your existing roof easily. The structure is already built, but we can build a new cabin with a double roof. Or we can add insulation to your attic space if you have one. That would help significantly. I don't have an attic, just the roof directly above the ceiling. I need a new cabin. This winter is proving that. The story spread rapidly through the Wind River Range. The Swedish engineer with the double roof. His cabin stayed warm in minus 30-degree weather. He used a third of the wood everyone else used. He'd proven that an air gap was better insulation than solid wood. People wanted to understand how. They wanted to see it. They wanted to build their own double roofs. Martin welcomed visitors throughout January. He showed them his roof construction. He explained the principles: heat transfer by conduction, air as insulation, optimal gap sizing, prevention of convection currents. Not everyone grasped the physics, but everyone understood the results. 31 degrees warmer. 1/3 the wood consumption. Sleeping comfortably in extreme cold. These benefits were tangible and compelling. By February, 9 families had asked Martin to consult on building cabins with double roofs. He agreed to help design each one. The principles were the same. Create a 3 to 4 inch air gap between ceiling and roof. Seal the gap to prevent air circulation. Provide minimal venting for moisture control. Keep the gap dimension consistent. The construction happened in summer 1919. Martin helped design 7 new cabins with double roofs. 2 families modified existing cabins by adding attic spaces with proper air gaps. The results the following winter were consistent. Every cabin with a proper air gap showed dramatic improvements. Interior temperatures increased by 20 to 35 degrees compared to conventional cabins with similar heating. Wood consumption dropped by 50 to 70%. Comfort improved enormously. The validation was complete. If you're seeing that the biggest heat losses aren't through walls but through roofs, and that the best insulation isn't expensive materials but understanding air gaps, then you need to subscribe to this channel right now. We're proving that physics beats products every single time. Hit that subscribe button and join us in learning what actually matters. Now let's dive into the science behind why Martin's roof gap was so effective. The physics of Martin's double roof involved understanding heat transfer mechanisms and air properties. First, the 3 modes of heat transfer. Heat moves in 3 ways: conduction, convection, and radiation. Conduction is heat moving through materials by molecular contact. Convection is heat moving by fluid motion. Air or water carrying heat from one place to another. Radiation is heat moving as infrared energy through space. All 3 modes were at work in cabin heating. Understanding which mode dominated in which location was key to efficient design. In Martin's cabin, hot air from the stove rose to the ceiling by convection. This is natural and unavoidable. Once the hot air contacted the ceiling, it tried to transfer heat through the ceiling by conduction. In a conventional cabin, the ceiling and roof were tightly coupled. Heat conducted through the ceiling boards, then through the roof boards, then radiated away to the cold sky. The total thermal resistance was low. Heat escaped easily. In Martin's cabin, the hot air contacted the ceiling. Heat conducted through the ceiling boards, but then it encountered the air gap. Air is an extremely poor conductor. Heat transfer through still air by conduction is about 1/100th as fast as through wood. The air gap was a massive bottleneck for heat flow. Heat could barely cross the gap. It accumulated in the ceiling area. The cabin stayed warm. Second, the R value concept. R value is resistance to heat flow. Higher R values mean better insulation. Wood has an R value of about 1.25 per inch. A typical roof with 8 inches of wood total thickness has R value of about 10. Martin's air gap was 3 3/4 inches. Still air has an R value of about 4 to 5 per inch, depending on exact conditions. So his gap had R value of 15 to 19. For less than half the thickness, more insulation value. But this only worked if the air couldn't circulate. If the gap was too large, convection currents would form. Hot air would rise on one side, cool air would sink on the other. The circulating air would carry heat across the gap by convection. The insulation value would plummet. The critical gap dimension prevented convection. For horizontal surfaces like roofs, the optimal gap is about 3 to 4 inches. Larger gaps allow convection. Smaller gaps don't provide enough insulation benefit. Martin's 3 3/4 inches was optimal. Third, the moisture management. Trapped air must be dry to insulate well. Water. Vapor in the air can condense when it contacts cold surfaces. Condensation reduces insulation value dramatically. Water conducts heat much better than air. Martin's vent holes allowed moisture vapor to escape. The vents were sized carefully, large enough to exhaust vapor, small enough to prevent significant air circulation. This kept the gap dry while maintaining the dead air insulation. Fourth, the cumulative effect of temperature gradient. In Carl's cabin, the ceiling temperature was perhaps 60 degrees when room air was 50 degrees. The roof exterior was minus 30 degrees. Total temperature difference of 90 degrees across maybe 8 inches of roof. Steep gradient, high heat flow. In Martin's cabin, the ceiling temperature was perhaps 75 degrees when room air was 79 degrees. The air gap bottom was maybe 74 degrees. The air gap top was maybe 35 degrees. The roof exterior was minus 30 degrees. The steep gradient was isolated to the 5-degree drop across the outer roof. The air gap absorbed most of the temperature difference, 39 degrees, across 3 3/4 inches of dead air. Because air conducts so poorly, this steep gradient in the gap didn't translate to high heat flow. Heat couldn't cross efficiently. The system worked beautifully. The mathematical analysis is revealing. Heat loss through a surface. Q equals U times A times delta T, where Q is heat loss in BTUs per hour. U is overall heat transfer coefficient. A is area. Delta T is temperature difference. For the same cabin size and the same inside-outside temperature difference, the cabin with lower U value loses less heat. U value is the inverse of R value. Higher R value means lower U value means less heat loss. Carl's roof, R value of 10, U value of 0.1. Martin's roof, R value of 30 to 35 total, including both roof layers and the gap. U value of 0.03. Martin's U value was about 3 times lower than Carl's. For the same inside-outside temperature difference, Martin lost about 1/3 as much heat through his roof. Since roofs account for 50 to 60% of total cabin heat loss, reducing roof heat loss by 2/3 reduces total cabin heat loss by approximately 40%. This explained why Martin used 1/3 the wood Carl used. He was losing 40% less total heat. Heating requirements are directly proportional to heat loss. Less heat loss means less heating needed. The 31-degree temperature difference between the cabins was the result of this efficiency difference. With similar heating input, Martin's cabin accumulated heat. Carl's cabin lost heat. At steady state, Martin's cabin stabilized at a much higher temperature. The comfort factor was also significant. In Carl's cabin, the ceiling was cold. Heat was actively escaping through it. The room felt drafty even without actual drafts. Cold surfaces radiate coldness. You feel it. In Martin's cabin, the ceiling was warm. Heat wasn't escaping. The room felt cozy. Warm surfaces radiate warmth. The psychological difference was substantial. The construction cost comparison was reasonable. Carl's cabin roof, approximately $100 in materials and labor. Martin's cabin roof, approximately $125. $25 additional investment. The operational savings were dramatic. Martin used about 20 cords per year for heating. Carl used about 60 cords, 40 cord difference. At 4 hours per cord for cutting, splitting, and hauling, that's 160 hours of labor per year. At any reasonable value for time, $25 paid back in the first winter. Every year after was pure profit. The durability was excellent. The double roof structure was actually stronger than a single roof. 2 sets of rafters cross-braced, more structural support. The air gap also protected the inner roof from temperature extremes. The outer roof bore the brunt of sun, rain, snow. The inner roof stayed at moderate temperature always. This extended lifespan. Martin's original double roof operated for 32 years before needing any repair. At that point, the outer shingles were replaced. Cost $40. The inner roof was still perfect. Total maintenance over 32 years, $40. A conventional roof would have needed replacement every 15 to 20 years in that climate. 2 full replacements over 32 years. Cost over $200. Martin's double roof was cheaper to maintain and performed far better. By summer 1920, 18 cabins in the region had double roof construction. By 1925, over 40. The technique spread throughout Wyoming and into Montana and Idaho. The designs varied. Some used different gap dimensions. Some used different ventilation strategies. Some combined the air gap with other insulation materials. But all followed the core principle: create a dead air space between ceiling and roof to maximize thermal resistance. The technology never went mainstream for typical reasons. It required understanding principles most builders didn't have. Explaining that trapped air insulates better than solid materials was counterintuitive. It also required careful construction, getting gap dimensions right, preventing convection, managing moisture. Builders who understood could execute it well. Those who didn't often created gaps that didn't work. But among mountain people who valued efficiency and understood the results, double roof construction became standard practice in some regions. Modern building science has validated Martin's approach completely. The optimal air gap for horizontal insulation is documented as 3 to 4 inches. Exactly what Martin calculated. Modern insulation materials often incorporate dead air spaces. Fiberglass and foam work by trapping air. Double-pane windows work by trapping air between panes. The principle is universal. Trapped air is excellent insulation. Martin understood this in 1918. We've since confirmed it with extensive testing and analysis. Martin Lindholm lived in his Wyoming cabin from 1918 to 1950, 32 years. During that entire time, he benefited from his double roof design. He was always warmer than neighbors, always used less wood, always more comfortable. In 1950, Martin moved to Cheyenne to live with his daughter's family. He was 78 years old. The cabin was sold and remained occupied for another 15 years. When it was finally torn down in 1965, the double roof was examined. The air gap was still perfect, 3 3/4 inches throughout. No sagging, no compression. The structure was sound. The construction had been excellent. Records of Martin's cabin exist in county archives. Building permits from 1918 document the unusual roof construction. The permit inspector noted, double roof structure with air space, unusual design but structurally sound. This notation is the only official documentation of Martin's innovation. A few photographs exist showing the cabin's unusually tall profile. The double roof made the cabin look taller than neighboring cabins. These photos are held by the Wyoming State Museum. Before we finish, I need you to understand something critical. If you're seeing that the best solutions often look stupid until proven, that trapped air beats expensive insulation, that understanding heat flow matters more than following conventions, then subscribe to this channel right now. We're preserving knowledge that most people have dismissed or forgotten. Hit that subscribe button and make sure you're learning what truly works. Now let's wrap up with what Martin's roof gap teaches us about building and efficiency. The story of Martin's roof gap teaches several profound lessons. First, the biggest heat losses often occur where you'd least expect. Most people focus on walls, thick walls, insulated walls, well-sealed walls. But in most structures, the roof is the biggest source of heat loss. Hot air rises. It concentrates at the ceiling. If the ceiling and roof don't resist heat, flow well, enormous amounts of heat escape. Martin understood this. He focused his effort where it mattered most, the roof. The result was dramatic efficiency gain. Second, counterintuitive solutions are often correct. Trapped air being better insulation than solid wood seems wrong. It violates intuition. Empty space shouldn't outperform solid material, but it does, because heat transfer depends on molecular density and motion. Air has few molecules and they're far apart. Heat can't conduct through it well. Solid wood has many molecules packed together. Heat conducts through it efficiently. The counterintuitive solution is the right solution. Third, precision matters in execution. Martin's 3 3/4-inch gap was precisely maintained throughout the roof, consistent dimension everywhere. This prevented convection currents. If the gap had varied, if some areas were larger, convection would have formed. The insulation would have failed. Good design requires good execution. Sloppy construction defeats good principles. Fourth, moisture management is critical in insulation systems. Trapped air only insulates well when dry. Water or water vapor degrades performance catastrophically. Martin's venting system managed moisture without compromising the dead air space. Small vents, just enough to exhaust vapor, not enough to allow circulation. This attention to detail was essential. Ignore moisture and the system fails. Fifth, the best solutions often require understanding multiple principles simultaneously. Martin had to understand conduction, convection, and radiation, air properties, optimal gap sizing, moisture dynamics, structural requirements. Integration of all these principles created the effective solution. Knowing one principle wasn't enough. He needed comprehensive understanding. Sixth, dramatic improvements are possible with minimal cost. $25 of additional lumber, maybe an extra week of construction time. These small investments created a 31-degree comfort improvement and 66% fuel reduction. The return on investment was extraordinary. We often assume big improvements require big investments. Martin proved otherwise. The 31-degree temperature difference between Martin's cabin and Carl's cabin was life-changing. Carl at 48 degrees was miserable, constantly cold, constantly burning wood, constantly exhausted from fire tending. Martin at 79 degrees was comfortable. Normal clothing indoors, normal sleep, minimal fire tending, same climate, same basic cabin size and construction, just a different roof. The economic analysis shows the power of efficiency. Martin spent $25 extra on construction. He saved 40 cords of wood per year. At 4 hours per cord, that's 160 hours of saved labor annually. Over 32 years, 5,120 hours. At any reasonable value for time, the payback on $25 was achieved in weeks. The total value created was enormous. The social dynamics followed the familiar pattern. Before winter, mockery. Everyone laughed at the double roof, called it stupid, predicted failure, called Martin overconfident. After winter, admiration. Everyone wanted to learn from Martin, build double roofs, benefit from his knowledge, recognition that the engineer knew more than the conventional builders. Innovation requires confidence to persist through mockery. Martin had studied building science. He knew his calculations were correct. He built according to principles, not conventions. When reality validated his approach, the mockery turned to respect. Martin's roof gap represents elegant application of fundamental physics. Heat transfer, theory, fluid dynamics, material properties, moisture science. These principles existed long before Martin. He didn't invent them. He applied them intelligently to solve a practical problem. The result was a heating system far more efficient than anything commercially available. Knowledge enabled him to build better than anyone could buy. The technology slowly faded after the 1950s and 60s. Modern insulation materials became available. Fiberglass, foam, rock wool. These materials trapped air in different ways but achieved similar R values. They were easier to install than building double roofs. Convenience won. But the principle remained valid. The best modern insulated roofs still use dead air spaces. Double-layer construction with gaps, Radiant barriers creating air spaces. The physics hasn't changed. We've just found different ways to implement the same principle. Martin's stupid roof gap kept his cabin 31 degrees warmer than everyone else's. It used 1/3 the wood. It provided comfort through the worst cold Wyoming could offer. It operated flawlessly for 32 years. It proved that 3 3/4 inches of trapped air was better insulation than 8 inches of solid wood. Martin was right, the mockers were wrong, and the difference was understanding. Understanding heat transfer, understanding air properties, understanding optimal gap sizing, understanding moisture management, knowledge that Martin brought from his engineering education, knowledge that he applied with minimal materials to create extraordinary results. Everyone laughed at his stupid roof gap. 2 roofs separated by air, wasted lumber, overcomplicated design, theoretical nonsense, until it kept his cabin 31 degrees warmer, until it cut his wood consumption by 2/3, until it proved that engineering principles beat conventional wisdom. Then they stopped laughing and started learning. That's how knowledge spreads. One unlikely solution at a time, one measured result at a time, one converted skeptic at a time. Martin's double roof warmed mountain cabins for decades. Then it was forgotten. Now we're remembering. The principle is simple. The results are extraordinary. We just have to choose understanding over convention, physics over tradition, knowledge over assumptions. Martin showed us how. The roof gap is still there in those old photos. 3 3/4 inches of empty air keeping people warm. The smartest stupid trick ever built.